Good day, everyone, and welcome to our next lesson. We are now on lesson 9 entitled Material Balances for Combustion Reactions. This is a continuation of our previous lessons wherein we defined the general way of solving material balance problems for reactive processes. Now, in this lesson, we are going in detail into one of the most common reactions in the industry, which is combustion. So let's begin. Let's first define the nature of combustion reaction. So you have already encountered combustion in your life, no, maybe once or more than once. Basically, anything that you are burning is experiencing combustion. In scientific terms, combustion is defined as a reaction that involves oxygen oxidizing a fuel. That's why when you react a fuel with gaseous oxygen, you produce oxides and a lot of energy. No, combustion is generally correlated with processes that require a large release of energy. It's called burning in simple terms. No, it's characterized by the release of stored chemical energy and the formation of oxides. And for combustion, we follow this general reaction wherein the fuel reacts with oxygen. Normally, we obtain oxygen from the air, and that produces oxides of the fuel plus energy. And normally, we are interested in the amount of energy that is being released by the combustion reaction. So next. Okay. The most common fuel used in industrial combustion are made of carbon, hydrogen, and oxygen. So those are the basic building blocks of fuels in the industry, together with trace amounts of sulfur, nitrogen, and miscellaneous metals as part of the minority. So when you have a fuel, expect that it would have carbon, hydrogen, and oxygen as one of its primary composition, because carbon and hydrogen are the parts of the fuel that can actually combust and can actually provide energy. So if we have a hypothetical fuel with a chemical formula CXHYOZ, you add that with a certain amount of oxygen, and we have here the generalized combustion reaction. You have your fuel plus oxygen yields. The oxide of carbon is CO2 for a complete reaction, and the oxide of hydrogen is water. And of course, we have here the plus energy, which is released in combustion reactions. We have two types of combustion reactions that we are interested in. We have the complete and incomplete combustion. This is what you have to remember in our problem-solving process. In our previous lesson, we have defined complete and incomplete reactions based on the value of their fractional conversion. So if you have a fractional conversion of 1, that means that you have a complete reaction. And if you have a fractional conversion less than 1, that means you have an incomplete reaction. So that's the same with combustion reactions. But for combustion reactions, we have specialized terms wherein when we are pertaining of complete combustion, we are referring to the products being the most oxidized form of the fuel. So if you have the basic carbon hydrogen fuel, the most oxidized form of carbon is carbon dioxide. The most oxidized form of hydrogen is water. And if you have some sulfur in your fuel, its most oxidized form is SO3. So if you see those substances in the product, no, or if those are the substances that you see in the product, that means that you have a complete reaction. Now, if you start seeing some components of the product stream that are not fully oxidized, examples of those are carbon monoxide, elemental carbon, and SO2, that means that you have a lack of oxygen in the process, or there is some inefficiency wherein the oxygen cannot get into the fuel efficiently. That's why you have an incomplete combustion. In incomplete combustion, what normally happens is that your fuel cannot sufficiently react with the oxygen supplied. That's why you cannot generate the highest oxidized products. A part of the carbon could be transformed to CO2, but also a part of it is transformed to carbon monoxide. That is a telltale sign of incomplete combustion. Okay? A common example of an incomplete combustion is when you are lighting or when you're burning a piece of paper. So what you normally observe when you burn a piece of paper is that, of course, you see the flames, and then above the flames, you see a column of black smoke. No? The black smoke is indicative of incomplete combustion because you are forming particulates and elemental carbon as part of your products. Of course, you're still forming carbon dioxide and water, but a part of your products now contain the less oxidized species. So that is what we term as incomplete combustion. Next. So here are just some important reminders whenever you are dealing with a combustion reaction. In majority of the problems that you will be encountering in combustion reactions, the oxygen is always the excess reactant. That's because we want to avoid incomplete combustion. And one of the ways for you to avoid incomplete combustion is to increase the amount of oxygen. So it's the excess reactant. Okay? Since oxygen is an important factor in the completion of combustion reactions, it is normally supplied at an excess. So therefore, the percent excess oxygen or percent excess air would be a very important variable to calculate for combustion problems. Okay? So air is the largest free source of oxygen because air is very abundant and it's free. But it also comes with nitrogen and other trace gases. So in fact, we have performed similar calculations earlier. No? When we are pertaining to air, we say that it's 79% by mole nitrogen gas and only 21% by mole oxygen gas. So that low concentration of oxygen means that whenever you are using air in a combustion process, you're also using the nitrogen from the process. But nitrogen is generally considered as an inert during combustion, meaning that we normally don't get a large combustion from the nitrogen, no? Because the combustion of nitrogen only happens at very, very high temperatures. Okay? So here at very high temperatures, nitrogen can be oxidized to its oxidized state. So you have NO, NO2, N2O, and etc. For our engineering calculations, we will be assuming that nitrogen is an inert and does not combust in the process. Okay, remember that. Okay, let's move on with the three types of fuel. We generally classify carbon-based fuels based on their state. Is it a solid, liquid, or a gaseous fuel? So in this lesson, we will only be discussing about liquid and gaseous fuels. Those are the easiest fuels to manage. I think solid fuels will be reserved for your chemical process industries course because the combustion of solid fuels is very complicated. It involves a lot of cases, a lot of different cases for different calculations. So each type of fuel has different combustion characteristics that may affect calculations, but they generally follow the same pattern of solving material balance problems. During our past few lessons, we have familiarized ourselves with the conduct of the extent of reaction, species balance method, and the atomic balance method. All of those would still be useful in this lesson. So in particular, the atomic balance method would mostly be the one that we are going to use for combustion problems. Okay. Gaseous and liquid fuels, such as natural gas, gasoline, LPG, and others, often require the least amount of percent excess air as they are easy to combust, which normally requires around 5 to 20% air. So that's the main difference between the gaseous and liquid fuels with the solid fuels such as wood, coal, and charcoal. No, wood, coal, and charcoal and other types of solid fuels are very hard to continuously combust because you need to grind them into very, very small particles for them to continue burning. No, you need to expose a larger surface area of the solid. They are almost always accompanied with a large percent excess of air, sometimes even more than 100% because of their difficulty of sustaining complete combustion. So what would happen if you did not supply the needed percent excess air? So there are several things that could happen. One, and the most likely thing that could happen is that you could be promoting incomplete combustion. Again, a telltale sign of you having incomplete combustion is your product stream contains less oxidized species such as carbon monoxide and even elemental carbon. No? So if you're seeing that in your products, one of the main remedies to do is to simply increase the percent excess air. Now, you might argue that if we increase the percent excess air, we would get a more complete combustion. Well, technically that is the case, but one thing to remember is that combustion reactions like this are normally useful in the industry as sources of energy. And the main source of energy coming from combustion is the heat energy. Now, if you're supplying with a very big amount of percent excess air, what that does is you are diluting the heat because you are introducing more air. So therefore, you are reaching lower and lower temperatures in your products or in your flue gas. So that is just one thing to ponder. Of course, we will not be discussing energy balances here. No, energy balances will be discussed in your thermodynamics course, but that's just something to think about percent excess air. Okay, let's briefly go into the flow chart of a combustion process before we discuss this flue gas. For combustion processes, normally the unit is called a burner. You can also call this a combustion chamber, no, an oxidation chamber, no, but generally we call this a burner. Your feed contains your fuel. Your fuel could either be the solid, liquid, or gaseous fuel. And another input to the process is the air. Now, we represent the air as a separate stream because normally in the process, the fuel and the air would be introduced in separate streams. No, they are not pre-mixed. Although there are some processes which are pre-mixing the fuel and the air, but for clarity purposes, let's separate the streams for the fuel and the air. So let's say, for example, that my fuel contains carbon and hydrogen only at a set percentage, no? And then the air, as you know, contains both oxygen and nitrogen. So what is the product of this process? In previous lessons, if this is a generic process, we would have called the product here as P. But since this is specialized in combustion processes, we will be calling the product as FG or flue gas. So we will come back to this diagram later. So what is the flue gas? The gaseous combustion products or the product to the burner unit are called the flue gas or the stack gas. You can use those two terms interchangeably. No, flue gas is just the same as stack gas. And so what is Orsat analysis? In one of our previous problems in the worksheet, there is one problem there wherein you're given the water-free analysis of the product. So that water-free analysis of the product is what we call here the Orsat analysis. The term Orsat analysis refers to the flue gas composition without water. Now, some of you might be asking, isn't water one of the primary products of combustion? Yes, it is. We are still maintaining that there is water in your flue gas, but the Orsat analysis reports the composition excluding the water. Okay? There is still water, but we are not including it in the Orsat analysis. The Orsat analysis was coined from the Orsat analyzer, which is an apparatus that can determine the composition of flue gas after the removal of moisture. The Orsat analyzer works by measuring the volume of the flue gas that was removed through a certain absorbent. So the first absorbent on the Orsat analyzer is usually the one that removes moisture, because moisture can interfere with the determination of carbon dioxide and sulfur dioxide. So we normally have to remove the water. That's why we have to report some flue gas under Orsat analysis. Okay? You can have additional reading on the Orsat analyzer so that you can have an idea of why it excludes or why does it need to exclude water. Okay? The Orsat analysis is synonymous with terms like water-free analysis, dry flue gas, and dry stack gas. So in some problems, whenever you encounter the term dry flue gas, you need to know that that is already an Orsat analysis. Okay? So this is just an important note here. This is just highlighting what I have said earlier. No? The Orsat analysis does not imply that there's no water in the flue gas. So oftentimes water is present, but it's just not part of the percentage composition. So you still have to factor in the water. I will be showing this in our computations later. Okay, let's begin the calculations with gaseous fuels. Now, gaseous fuels are the easiest combustion calculations to manage. So some of the commonly encountered gaseous fuels include natural gas and biogas. In these types of problems, atomic balance method is the easiest approach in solving such problems because we don't need the chemical reaction itself, no? Or you don't need to determine the exact chemical composition or the exact chemical identity of your fuel. You just need a composition. Let's have this example here. Report the Orsat analysis of the flue gas if natural gas containing 85.6% methane, 5.45% CO, and 8.95% hydrogen is combusted with 20% excess air. So let me first jot down the given. Okay, we have here the given for our first example. So we have the classic burner, no, wherein the feed is given as 85.6% methane, 5.45% carbon monoxide, and 8.95% hydrogen. Our air is supplied in 20% excess, and we have oxygen and nitrogen in our air. Now, the first step when you encounter these types of problems is, what do you expect to be the contents of your flue gas? Now, the contents of your flue gas would be largely determined by the contents of your fuel. You simply need to write the basic combustion reactions for every component of your fuel that can be combusted. So let's start with the methane. CH4 can be combusted. If we add that with oxygen, we will get carbon dioxide and water. And you need to balance this equation. So to balance, we need to multiply this by 2 and multiply oxygen by 2. So we now have a balanced equation for methane. So now the products here are carbon dioxide and water. So of course in the flue gas you expect to have carbon dioxide and water. Next component is carbon monoxide. Now carbon monoxide or CO is not yet fully oxidized, therefore it can still react with oxygen to form carbon dioxide. So basically when you have a carbon-based compounds, as long as it's not carbon dioxide, it can still be combusted. Okay? If you have carbon dioxide in your feed, that's the only time wherein it can no longer be combusted. So in this case, balancing the equation we multiply this by 1/2, no, the oxygen. So since we have carbon dioxide in the product, we already have the carbon dioxide in the flue gas. Last one, hydrogen gas. If we react that with oxygen, we get water. Balancing, we multiply oxygen by 1/2. Okay, so the content of our flue gas is only carbon dioxide and water, but remember that air is being supplied in excess, therefore we expect to have an excess of oxygen. That's why we still have oxygen in the flue gas, and nitrogen in this case is an inert, so we still expect to have nitrogen in the product. Now, when it comes to your fuel, no, if the problem does not explicitly state that it's an incomplete reaction or that not all of your fuel is being consumed, you can safely assume that there's no longer fuel in your flue gas. So you don't have to place CH4, CO, and hydrogen in your flue gas. Our first assumption is that all of the fuel is being combusted. So why is it safe to give that assumption? That's because we are supplying a sufficient amount of percent excess air. Remember, for gaseous fuels, we only need around 5 to 20% of percent excess air in order for us to completely combust the fuel. Okay, so in this case, we have 20% excess air. It's enough to assume that our fuel will be completely combusted. That's also that's also the reason why there's no carbon monoxide in the flue gas, no? Because we're assuming complete combustion. Okay, next, we are required to determine the flue gas composition or the flue gas Orsat analysis. Again, the Orsat analysis will just exclude the water. Okay, now let's name all of our unknown parameters. So oxygen is unknown, that's N1. Nitrogen is N2. CO2 is N3. Water N4. Oxygen N5. And the nitrogen in the flue gas is N6. Now, right out of the bat, you see that I have mentioned earlier that nitrogen is an inert, or is generally considered as inert in combustion processes, meaning it does not participate in the reaction. No? It can only combust at very, very high temperatures. So we will be assuming here that nitrogen gas is an inert. Therefore, we can say that N2 is equal to N6, because whatever nitrogen comes in, it would also be the amount of nitrogen that's coming out. Okay? So to start the solution, we set the basis. A very good basis here would be in the feed. So let's see if there's no given. Okay, we're not given the amount of the feed, so we can assume a basis for the feed. Let's say 100 moles. Now, why did I use moles instead of grams? Remember, for gaseous substances, whenever you are given a percent composition and there's no specification if that's percent by mole or percent by mass, you are to assume that that is percent by mole because it's a gas. Okay? So after setting our basis, we can now proceed with determining the most important parameter in combustion reactions, which is the NO2 theo. If you'll remember on our past lessons, the number of theoretical moles of the substance is important for us to determine the percent excess of the substance. No? So in this case, you're given the percent excess. You need to determine the NO2 theo in order for you to get the amount of oxygen being fed into the process. So how do we solve the NO2 theo? Now, if you take a look at your developed equations for your fuel, you have three equations, one for methane, one for CO, and one for hydrogen. And all those three equations are all using oxygen. That means that in your NO2 theo, you should have three terms, each term corresponding to a component of the feed. So let's start with methane. We have 85.6 mole of methane. If you take a look at the balance equation, there is 1 mole of methane for every 2 moles of oxygen. So in these types of balances, your goal is just to stop at the number of moles of oxygen. So this is already our first term. Next, second term is for carbon monoxide. We have 5.45 mole of carbon monoxide. And based on the balance equation, for every 1 mole of carbon monoxide, there is 1/2 mole of oxygen. By the way, if you have chosen to balance your chemical equations with the least whole number coefficients, so that's also fine. No, it will not change our answer. Last term is for hydrogen. So we have 8.95 moles of hydrogen. And from the balance equation, 1 mole of hydrogen is equivalent to 1/2 mole of oxygen. In this case, you really have to make sure that your combustion reactions are balanced before you proceed. Because if they're not balanced, then you are automatically wrong in the NO2 theo. Okay? So solving for NO2 theo, what do we have? 85.6 times 2 plus 5.45 divided by 2 plus 8.95 divided by 2. So our theoretical number of moles of oxygen is 178.4 moles O2. Theoretical. So why is this important? No, this is important because we will be using this in the definition of the percent excess. So going back to the percent excess, which we are given the value 20% or 0.2. If you'll remember, the definition of percent excess is the number of moles fed or the number of moles input minus the number of moles theoretical all over the number of moles theoretical. So the number of moles of oxygen fed to the process is N1 minus theoretical is 178.4 all over theoretical. We can immediately solve for the value of N1. So this is 178.4 times 0.2, and then 178 plus this one, plus 178.4. Okay, our N1 is 214.08 moles oxygen fed. That is already the value of N1. Now, from this value of N1, you can immediately determine the value of N2, because remember, the oxygen and nitrogen in the air exists at a constant ratio. There's 21 moles of oxygen for every 79 moles of hydrogen in the air. So what you're going to do for you to solve for N2, so you simply multiply this by the ratio 79 over 21. That corresponds to 79 moles of nitrogen for every 21 moles of oxygen. So if you solve this, you get times 79 over 21, 805.35 moles nitrogen fed. So this is your N2. Okay? You will be seeing this same pattern for other problems we're in. The first step that you need to calculate is the NO2 Theo, because that gives you a gateway for the percent excess if it's given, for you to be able to solve the input oxygen and the input nitrogen to the process. Okay? Since N2 is equal to N6, we can say that N6 is equal to 805.35 moles of nitrogen as well. So from that, we already have a value of N1, N2, and N6. And we can now proceed with the elemental balances. Okay, so let me first erase some parts. We just need the values of N1, N2, and N6. So let me write them here. N1 is 214.08. N2 and N6 is 805.35. Okay. So after you're done with the NO2 Theo, you proceed with the elemental balances or the atomic balances. Let's start with the carbon balance. So what is your carbon balance in this case? You have 85.6 from CH4 plus 5.45 from the CO in the feed equals, in the product side, you have N3. So immediately, we have the value of N3 as 85.6 plus 5.45. 91.05 moles carbon dioxide. We're done with N3. Next, hydrogen balance. What is our hydrogen balance? So in the feed, we have methane, that's 85.6 times 4, plus hydrogen, 8.95 times 2, equals, in your flue gas, you have water, that's 2 and 4. We can now solve for the value of N4. 85.6 times 4 plus 8.95 times 2 divided by 2. 180.15 moles H2O. We're done with N4. And lastly is N5. For N5, we are going to perform the oxygen balance. Now take note that for majority of combustion reaction problems, when you are performing elemental balance, you always start with the carbon balance, because that almost always gives you an answer for one of the unknowns. Normally it's for carbon dioxide, no? And the last balance that that you need to make is the oxygen balance. You want to have the oxygen balance at the very last of the balances because oxygen balance is the longest. No? So let's see. In the feed, you have 5.45 moles of CO. That's 5.45 plus the oxygen coming from the air, that is 2N1. So 2 times 214.08 is equal to, in the product side, or in the flue gas, 3 of your components have oxygen. So that's why this is a very long equation. No? So that's 2 times N3 for carbon dioxide, 91.05, plus N4, 180.15, plus 2 N5. Now we can solve for N5, or the amount of oxygen. So that is 5.45 plus 214.8 times 2 minus 2 times 91.05 minus 180.15 all over 2. So N5 is 36.4 moles oxygen. So we're done with the atomic balances. No? So you see that our first approach was to determine NO2 Theo and then fiddle with the value of the percent excess oxygen. And then after that, you can directly proceed with the elemental balances. So this is just the same approach, no, with the previous problems for material balance problems with reaction, but this is much more specialized for combustion reactions. So of course, the problem requires us to get the Orsat analysis. So I will be highlighting how you get the Orsat analysis. So you simply compile all of the components that have something to do with the Orsat analysis. So it's everything in the flue gas except water. Just simply CO2, O2, and N2. That's it. We get the number of moles. CO2 is 91.05. O2 is 36.4. N2 is 805.35. Get the total. 36.4 plus 91.05 plus 805.35. Okay, total 932.8, and you can now get the either the percent by mole or the mole fractions. Let's do the percent by mole. 932 so that's 91.05 over 932.8. You have 9.76%, 3 significant figures, okay? And then 36.4, 3.90%, and then 805.35. 86.3%. This will not be exactly 100% because your percent by mole of nitrogen is only 1 decimal place long. So that's okay. No, if we are sticking with significant figures, so this is already okay. Okay, so that is how we solve combustion reaction problems for gaseous fuel. So it's basically the same process as our previous lesson. Next, we have the liquid fuels. Commonly encountered liquid fuels include diesel, gasoline, and kerosene. So as with the material balance involving gaseous fuels, when you're encountering liquid fuels, the atomic balance method is still the easiest approach in solving such problems. There's not much difference between those involving gaseous and liquid fuels, no? The main difference is that for gaseous fuels, you would normally encounter fuels that are given in percent by mole composition because it's a gas. For liquid, it's in percent by mass or percent by weight because it's a liquid. Let's try to solve this example. The composition of a given liquid fuel by weight is 84.8% carbon and 15.2% hydrogen. Determine the weight of air needed to completely combust 1 kilogram of the fuel, as well as the complete combustion of the flue gas. As well as the complete composition of the flue gas if 15% excess air is supplied. So let's list the given. Okay, here is our given to the process. We are given the burner. We have 1 kilogram of the fuel with the given composition in percents by mass. Our percent excess air is 15%. What we are required to determine is the mass of air needed to completely combust our feed, and of course the flue gas composition. It's not asking for an Orsat analysis, so we are going to include water in the flue gas analysis. So let's begin by setting our basis. Our basis is 1 kilogram of the fuel, and the fuel here is given in, or the composition of the fuel here is given in percent by mass. Let's begin with the NO2 Theo. Now, remember that for NO2 Theo, what's important for us is to determine the chemical reaction for combustion of your fuel. In this case, your fuel is given only as an elemental composition. We call this elemental composition because it already gives you the percent by mass of the elements in the fuel. No? So you have 84.8% carbon and 15.2% hydrogen. In that case, it's actually easier for you to set up the combustion reactions because you are just combusting single elements. For example, for carbon, you simply react that with oxygen and you form carbon dioxide. And this is already a balanced equation, 1:1:1. And for hydrogen, we react that with oxygen to form water. To balance, we multiply this by 2. We multiply this by 1/2. So those are our two chemical equations that we will be using for NO2 Theo. Okay, so solving for NO2 Theo, the first term will be for the carbon. Okay, so one of the most common mistakes in solving for NO2 Theo is some students forget that they are dealing with masses and that they need to convert the masses to moles before they can solve for NO2 Theo. Okay, so in here we have 0.848 kilograms of carbon coming from our basis and from the composition of the fuel. You first have to convert that to moles of carbon. So that's 12 kilograms of carbon is to 1 kilogram mole or kilomole of carbon. And then you can proceed with the balanced equation for the stoichiometry. That's 1 kilomole. That's 1 kilomole of carbon equivalent to 1 kilomole of O2. Plus, for hydrogen, you have 0.152 kilograms of hydrogen, converting to moles. That's 1 kilogram of hydrogen per 1 kilomole hydrogen. And then from the balance equations, you have 2 kilomoles of H for every 1/2 kilomole of O2. And if you take a look at the cancellation of units, you will be left with kilomoles of oxygen, which is our target. So our NO2 Theo is 0.848 divided by 12 plus 0.152 divided by 4. Okay, our NO2 Theo is 0.109 kilomole O2. Now, for our first required, we want to determine the mass of air needed. So therefore, this kilomoles of oxygen needs to be converted to kilomoles of air. So what is our conversion ratio? So in our previous example, we used the conversion ratio 79/21 in order for you to convert the kilomoles of oxygen to kilomoles of nitrogen. But in this case, we want this to be directly determined as NO2 N air Theo, or the number of moles of air theoretical. So we're going to use the ratio 100 kilomoles of air. For every 100 kilomoles of air, there is 21 kilomoles of oxygen. So what we will get here is already the number of kilomoles of air that's required. So that's times 100 divided by 21. 0.517 kilomoles air, theoretical. Okay, and then what's needed is we simply have to convert this to mass using the molecular weight of air. For simplicity, we're going to use 29 kilograms per kilomole as the molecular weight of air. Although if you want, you can use the more exact 28.86 kilograms per kilomole. 29 kilograms for every 1 kilomole of air. We get the answer to the first required as 15 kilograms. How do we interpret this? No? We interpret this as we need 15 kilograms of air, theoretically, to completely combust 1 kilogram of our fuel. And that's not factoring our percent excess. No? Because if you're asked for the theoretical mass of air needed, then you go with the theoretical number of moles of air that's needed. Okay? So this is one of the answers. No, 15 kilograms of air, theoretical. But if you're asked to determine the exact or the actual amount of air that's being needed to combust, then you have to factor in the percent excess. Okay. Let's first list one of the answers. So the mass of air needed is 15 kilograms of air, theoretical. For our balances, we will be needing the value of NO2 Theo. So I'm going to write here NO2 Theo as 0.109 kilomoles of oxygen. And then let's erase some of this. We are now going to be using the definition of percent excess. So percent excess is 15%, so that's 0.15 is equal to the amount of oxygen. We forgot to determine the components of your flue gas. So your flue gas in here should contain CO2 coming here, H2O coming here, and then you have excess oxygen and then excess nitrogen. Okay, let's label the unknowns: N1, N2, N3, N4, N5, and N6. So going back to the percent excess, that's 0.15 is equal to the amount of oxygen fed, that's N1, minus the oxygen theoretical, 0.109 over 0.109. We now solve N1 as 0.15 times 0.109 plus 0.109. 0.125 kilomoles of O2 fed. That's your N1. And for us to get the N2, again, we simply multiply this by the ratio 79 over 21. .472 kilomoles nitrogen. So we now have values of N1 and N2 as well as N6, because in this case N2 is still equal to N6. Okay, now with the balances, let's have the carbon balance. This is another part of the problem solving wherein you have to be very careful. The atomic balances are very dependent on the number of moles, not on the mass. So you're given here 84.8, that is mass, not moles. So we have to convert that to moles first. And the way we're going to do that is to simply divide the mass with the molecular weight. So I'm going to do that straight in our balances. So for the carbon, we have 0.848. This is kilograms of carbon. We divide that with 12 kilograms per kilomole so that the entire ratio will now be in kilomoles. Okay? That's equal to N3. Now you might be asking, why did I not divide N3 with the molecular weight? That's because the flue gas is already understood to be in mole basis. And our fuel is in mass basis. That's why we have to divide the feed by the molecular weight. Okay? So from this, we now determine N3 to be 0.848 divided by 12. 0.0707 kilomole CO2. Okay, next, hydrogen balance. Again, the hydrogen in your feed is in mass, so that's 0.152 kilograms divided by 1, the molecular weight of hydrogen, is equal to 2 N4. From here, we get N4 as 0.152 divided by 2. 0.076 kilomole H2O. Next, oxygen balance. I hope you're sensing a pattern here, no? We start with the NO2 Theo, and we end with the atomic balances. And in your atomic balances, you start with the carbon and end with the oxygen balance. So oxygen coming from your feed is coming from the air. That is 2 times N1, 0.125, is equal to 2N3. Let's already substitute N3. From carbon dioxide, that is 0.0707, plus N4, 0.076, plus 2N5. Okay, and solving for N5, that's 2 times 0.125 minus 2 times 0.0707 minus 0.076 divided by 2. So our remaining oxygen in the product is 0.0163 kilomole oxygen. Okay, and that's it. The only thing that you need to do now is to determine the flue gas composition. So in here, we get all of the components of the flue gas: CO2, H2O, N2, and O2. No? This is not an Orsat analysis, so you have to include water in the analysis. And I will be leaving that to you. Okay, so you see, it's just the same approach. What's mainly different is our conversion from mass to moles. So remember to always check in your atomic balances and in your NO2 Theo. Do not forget to convert mass to mole before performing the balance. Okay, let's proceed. We have here a list of some of important cases that you always have to remember, because if you don't remember this, then your balances would automatically be wrong, no? Because we are very dependent on the value of the NO2 Theo. If oxygen is present in the fuel in any form except in water, the amount of oxygen in the feed needs to be subtracted from NO2 Theo. Okay? We are talking about the oxygen coming from the fuel. So to illustrate my point, I have here an example. Determine the theoretical amount of air needed to completely combust 100 moles of the following fuels. Let's try the first one. We want to determine the theoretical amount of air needed to completely combust 100 moles of ethanol. Let's see. Okay, we have here the given for the burner utilizing ethanol as the fuel. If we are going to write its combustion reaction, we write C2H5OH plus O2 yields CO2 plus H2O. So to balance, we multiply this by 2. Hydrogen is 6, we multiply this by 3. Your total oxygen is 7. 4, 5, 6, 7 minus 1, that's 6. We multiply this by 3. Okay, so for this equation, we can solve for the NO2 Theo. We just want to determine the NO2 Theo for this illustration. So if you are given a particular fuel that you know the composition or you know its chemical formula, in this case, we know the chemical formula of ethanol, there is no modification to the way on how you obtain the NO2 Theo. Okay? We still perform stoichiometry to determine how much oxygen are we going to need. So this is 100 moles of ethanol. And then based from the balance equation, for every 1 mole of ethanol, we are using 3 moles of oxygen. So this is 300 moles O2 Theo. So there's nothing different there. Okay? But what if the given is of a different set? Let's move on to the next one. A gaseous mixture of 50% CO2, 30% CO. So let me first list this. 50% CO2, 30% CO, 10% H2, 5% O2, and then 5% N2. Okay. Again, you're faced with the burner. You have 100 mole of your fuel. You're tasked to determine the NO2 Theo. Now, you see that there is an oxygen in the fuel. So let's highlight that. This oxygen from the fuel is different from the oxygen in the air because remember, normally the air is injected separately with the fuel. So if there's already oxygen in the fuel, that needs to be subtracted from the required oxygen coming from the air, no? And that should be reflected on your NO2 Theo. So let me show you how to do this. First, examine your fuel. Which among those compounds is combustible? So first, CO2 is no longer combustible. No, it's the most oxidized form of carbon, but CO is still combustible. So that's CO plus O2 yields CO2. To balance, that's times 1/2. Next is hydrogen. So hydrogen is still combustible. Next, oxygen. So oxygen is not combustible, but we have to subtract this later. And then finally, the nitrogen is not combustible. So all in all, we are just looking at 2 terms in our NO2 Theo plus another term for the subtraction of oxygen. So this is how it goes. If we have 30 moles of CO, by stoichiometry, 1 mole of CO is equivalent to half mole of O2, plus you have 10 moles of hydrogen, and then for every 1 mole of H2, that's equivalent to half mole of O2. And then minus, okay? Take note of this minus term. We subtract here the 5 moles of O2 that was initially present in your feed or in your fuel. Remember that this 5 moles of fuel should come from, that 5 moles of oxygen should come from the fuel or the feed. And this is very different from the oxygen from the air. That's why we are subtracting it. Okay? So let's solve this. We have 30 divided by 2 is 15 plus 5 minus 5, that is 15. So our NO2 Theo is 15 moles of O2. If you did not include this minus 5 moles O2, then you are automatically wrong because your answer in here would then be 20 moles of oxygen. So if you're wrong with the NO2 Theo, you would also be wrong with the percent excess oxygen, and you would also be wrong in your elemental balances. Okay, so please remember that this is very important. If you have free oxygen, or if you have O2 as part of your fuel, you have to subtract that from your NO2 Theo. Let's check the next scenario. A gaseous mixture of 90% CH4 and 10% water. Okay. So your fuel is now 90% CH4, 10% water. This is what we call a wet fuel. meaning there is water in your fuel. So this water is in the form of a vapor. Okay? So out of those two components of the fuel, the only thing that's combustible is the CH4. So we write its balance equation. CH4 plus O2 yields CO2 plus H2O. Multiply this by 2, balanced. For the NO2 Theo, we proceed as usual. So you might argue, no, there is oxygen in the fuel, and that oxygen is part of the water. In this case, you don't have to subtract the amount of oxygen in water in your NO2 Theo because it's already part of water. Okay, so our exemption to the rule is if the oxygen is present as water, no need to subtract from NO2 Theo. So our solution here would simply be 90 mole of CH4, and then from the balance equation, for every 1 mole of CH4, you have 2 moles of oxygen. Your NO2 Theo is 180 moles O2. No need to subtract. Okay, so I hope you see the difference from this case from the previous case. In the previous case, the reason why we subtracted, that's because we have free oxygen or free gaseous oxygen in the fuel. In this case, the oxygen is not free, it's part of water. Okay, last one. A dry liquid fuel with a given elemental analysis. For this instance, let's say that we are not given 100 moles. Let's say that we are given 100 grams of the fuel because we're talking of a liquid fuel. So let me first write the given. That's 70% carbon, 15% hydrogen, 10% oxygen, 3% S, and 2% N. Okay. Now, sorry, this is not 100 moles. This should be 100 grams. Now, we will proceed as usual. We will be picking the elements that can be combusted. So in this case, carbon can be combusted, and the equation is C plus O2 yields CO2. Hydrogen plus O2 yields H2O. So to balance, that's times 2 times 1/2. Oxygen cannot be combusted. Sulfur can be combusted. So our equation is S plus O2 yields SO2. Now, normally for sulfur, we go to SO2 and not directly to SO3 because the combustion of sulfur to sulfur dioxide is much more thermodynamically favorable than going straight to SO3 without a catalyst. Okay? So for the base case scenario, you always use SO2 as your product for sulfur. And lastly, nitrogen is assumed to be non-combusting. Okay, so we don't include that. In this case, so some things to be very careful of is the given says that you have a dry liquid fuel. That means that your liquid fuel here does not contain water. And the implication is the oxygen present here is not coming from water. So we still have to subtract the oxygen coming from your fuel. Okay? So this is how we solve for this one. Now, we are in mass basis and our given is 100 grams. We first need to convert the mass to moles before we can solve for the NO2 Theo. So I will be doing that directly. So that's 70 grams of carbon divided by 12. So this gives us the number of moles of carbon. Okay, mole carbon. And then stoichiometry, 1 mole of carbon is to 1 mole of O2 plus hydrogen. You have 15/1, this is moles of hydrogen, times for every 2 moles of H, there is 1/2 mole of O2. Next, sulfur, plus 3/32 moles sulfur. For every 1 mole of sulfur, there is 1 mole of O2. Next, we need to subtract the oxygen that's present in the feed. Now, take note that the oxygen in the feed is in the form of oxygen or elemental oxygen. It's not in the form of gaseous oxygen, which is O2. So you have to factor that into account. Okay, so that we have 10 grams of oxygen divided by 16. So we have here moles O, and then to perform the stoichiometry, we need 2 moles of O to form 1 mole of O2. This is the thing that confuses a lot of people. You have to convert from elemental oxygen to gaseous oxygen. So do not forget this conversion. You have to divide by 2. No? We want everything to be in moles of O2. So if you take a look at our numerators here, it's all moles of O2. Okay? So let's solve. This is 70 over 12 times 1 plus 15 over 4 plus 3 over 32 times 1 plus 10 divided by 16 divided by 2. So our NO2 Theo is 9.99 mole. Okay, so I have shown you different scenarios for the inclusion of oxygen in the fuel and when not to subtract that from your NO2 Theo. Okay. So if you have further questions or if this part is unclear to you, you can message me and then ask me if you need to subtract oxygen from your NO2 Theo. Okay, we have here more problems. A mixture of 75% propane and 25% H2 is burned with 25% excess air. Fractional conversions of 90% of the propane and 85% of the hydrogen are achieved. Of the propane that reacts, 95% form CO2 and the rest form CO. Report the composition of the flue gas through an Orsat analysis. So I think you can already handle these types of problems. So in here, you have a gaseous fuel. So you simply follow our steps for the gaseous fuel. You are already given the percent excess air, which is 25%. So you already know what to do. First, you determine, first, of course, you draw the diagram and then label of the given and then give a basis. So what is a very good basis here? If you take a look at the problem, a very good basis here would be in the feed, because you're given the composition of the mixture. So you can use 100 moles of the feed or 100 moles of the fuel as your basis. After you have set your basis, so you have drawn your diagram, you have set your basis and labeled all of the unknowns, you go straight to the determination of the NO2 Theo. In this case, there's no oxygen in the feed or in the fuel, so you don't have to subtract oxygen. After the NO2 Theo, you go to the percent excess air to determine how much oxygen is fed to the process, and then you process the values of the fractional conversion of the propane and of the hydrogen, and then you perform all of the elemental balances. Okay, now take note that in problem number 1 you have CO in your product or in your flue gas. So your flue gas here would contain CO2, CO, H2O, O2, and N2. Now, how much CO2 will be formed? How much CO will be formed? It's stated here. 95% of the propane that reacts will form CO2 and the rest will form CO. So factor that out in your calculations. Okay, number 2, 100 kilogram moles per hour of a natural gas mixture of the given composition. You have methane, ethane, propane, and butane is burned in a furnace with 17% excess air. Determine the required volumetric flow rate of air, assuming it enters the furnace at 30 degrees Celsius and atmospheric pressure, and determine the composition of the flue gas, assuming complete combustion of the fuel. So this is just the same problem. No, this is just the same material balance involving a gaseous fuel, wherein you are required to determine how much air enters the process. So again, You draw the diagram, you label all of your unknowns, you determine the NO2 Theo. For the NO2 Theo here, all of the components of your fuel are combustible. No, methane, ethane, propane, and butane are all combustible. You simply have to write their balanced combustion reactions. You're given the percent excess air. So simply solve the number of moles of air fed, and then convert that to volumetric flow rates. Especially, you are already given the temperature and atmospheric pressure. So you simply use the ideal gas law. Okay? And finally, a problem involving a liquid fuel. So a liquid fuel containing carbon and hydrogen only is burned with excess air. You're given the Orsat analysis of your flue gas. So you have CO2, CO, O2, and then N2. And determine the liquid fuel composition in mass fractions and the percent excess air used. So this is just a reverse problem wherein you're given the composition of your flue gas and your unknowns are your feed. Okay, so in your fuel, you have carbon and hydrogen as your unknowns. In the air, you have the oxygen and nitrogen as your unknowns. Then you can, so in here, you can go straight with elemental balances. And you can easily find the composition of the fuel. Okay, so these 3 problems will be your worksheet number 7. Worksheet number 7 will be due next week. So you first focus on your exam number 2. So by the way, the combustion reactions is not part of exam number 2. It's part of exam number 3. Okay, so you first focus on exam number 2, and you can submit this worksheet number 7 next week. Okay, that's it for this lesson. I hope you have learned something, and if you have any questions, feel free to message me. Okay, and as always, stay safe.